Have you ever looked up at the night sky and wondered if we're truly alone in the cosmos? Picture a world where not one, but two suns rise each morning, casting twin shadows across alien landscapes. Or imagine standing beneath a sky not of water droplets, but of falling diamonds, glittering as they descend through an atmosphere thick with possibilities. These aren't scenes from science fiction, they're real places, distant exoplanets orbiting stars light years away from us, each one a potential cradle for life as we've never known it. Today, we embark on an extraordinary journey to explore the top 30 planets beyond our solar system that could host alien life, worlds where the conditions might just be right for something or someone to thrive. This quest is more than a scientific curiosity, it's a deeply human one. For centuries, we've gazed at the stars and asked the same timeless questions. Are we unique? Is Earth the only world blessed with the delicate, miraculous balance that allows life to flourish? Or are there others out there circling distant suns, perhaps even looking back at us and wondering the very same thing? Every discovery of a new exoplanet brings us one step closer to answering these profound questions, and in recent years, astronomers have found not just a handful, but thousands of these distant worlds. Some are scorching hot, others frozen solid, but a rare few exist in what scientists call the habitable zone, the perfect distance from their star where liquid water and maybe life could exist. Join me as we dive into the mysteries of the cosmos, exploring alien oceans hidden beneath icy shells, atmospheres rich with the chemical signatures of biology, and landscapes so strange they challenge everything we thought we knew about planets. We'll count down the top 30 most promising candidates, from super-Earths with crushing gravity to watery worlds where life might swim in global seas. This isn't just a list, it's an invitation to wonder, to explore, and to dream. By the end of our journey, you'll not only have discovered some of the most fascinating places in the universe, but you might just see the night sky a little differently, knowing that among those twinkling lights, there could be worlds waiting to be found and life waiting to be discovered. Just 4.2 light-years from our own solar system, a world orbits a star so faint it's invisible to the naked eye from Earth, yet it holds a title of immense significance. Proxima Centauri b is our closest known exoplanet, a next-door neighbor in the grand scale of the cosmos, residing snugly within the habitable zone of its parent star, Proxima Centauri. This places it in that tantalizingly narrow band of space where temperatures could theoretically allow for liquid water to pool and flow on its surface. With a mass estimated to be just 1.3 times that of Earth, it's what astronomers classify as a rocky super-Earth, a type of world that feels both familiar and profoundly alien. But the potential for life here is locked in a constant struggle with the planet's harsh reality. Proxima Centauri is a red dwarf star, a much smaller and cooler type of star than our Sun. Because of this, its habitable zone is incredibly close in. Proxima b completes a full orbit around its star in just 11.2 Earth days. This intimate dance likely results in a phenomenon called tidal locking, much like how our moon always shows the same face to Earth. This means one hemisphere of Proxima b is locked in perpetual, searing daylight, while the other is plunged into an eternal, frigid night. The only region that might enjoy anything resembling a temperate climate would be a thin twilight band, the terminator line where these two extreme worlds meet. The challenges don't end there. Red dwarf stars are notoriously volatile, known for unleashing massive stellar flares that bombard any nearby planets with intense ultraviolet and X-ray radiation. Proxima Centauri is particularly active in this regard. A flare from this star could be hundreds of times more powerful than anything our Sun produces, potentially stripping away a planet's atmosphere over billions of years and bombarding its surface with radiation levels lethal to life as we know it. So the central question for Proxima b becomes a fascinating puzzle. Could any atmosphere have survived this relentless assault? If it has held on to a thick enough envelope of gases, it's possible that atmosphere could redistribute heat from the day side to the night side, moderating those extreme temperatures and perhaps even creating pockets of habitability. It's a world of stark contrasts and dramatic possibilities, a reminder that the potential for life is often a story of resilience against incredible odds. While our closest neighbor presents a story of extremes, the TRAPPIST-1 system offers a narrative of astonishing abundance. Located nearly 40 light-years away in the constellation Aquarius, this system isn't home to just 1 or 2 planets, but a magnificent family of 7 Earth-sized worlds, all dancing in a delicate gravitational harmony around their faint, ultra-cool dwarf star. And of these 7 siblings, one stands out as a rock star in the search for life, TRAPPIST-1e. This world is a jewel, a prime candidate that checks so many of the boxes on our habitability wish list that astronomers can hardly contain their excitement. What makes TRAPPIST-1e so special starts with its foundation. Its size and mass are almost identical to Earth's, suggesting it's a rocky world with a solid surface you could theoretically stand on a familiar stage for the potential drama of life to unfold. But its most compelling feature is its address. It orbits perfectly within its star's habitable zone, that not too hot, not too cold region where temperatures could allow for liquid water to exist in a stable state on the surface. Unlike the potentially tidally locked Proxima b, some models suggest TRAPPIST-1e might even experience a day-night cycle, slowly rotating as it journeys around its star. This orbital real estate opens up thrilling possibilities. With the right atmospheric conditions, TRAPPIST-1e could boast a breathtakingly temperate climate. Scientists speculate it might host vast global oceans, its surface a shimmering blue marble much like our own homeworld viewed from space. The chemistry for life as we understand it could be present, all simmering under the gentle glow of a star that appears larger in its sky than our sun does to us, yet shines with a dim, warm, reddish light. The view from its surface would be unlike anything we know, with its sister planets tracing graceful, close orbits across the heavens. Some would appear as large as our moon, their features potentially visible to the naked eye in a perpetual celestial ballet. Yet, this promising picture isn't without its own set of cosmic challenges. Its parent star, like Proxima Centauri, is a red dwarf prone to flaring. The planet's proximity to its star also means it is likely bathed in tidal forces that could drive significant volcanic activity, shaping a dynamic and potentially unstable surface. The true nature of TRAPPIST-1e, whether it's a water world, a rocky desert, or something entirely unexpected, hinges on one critical unknown: its atmosphere. The next generation of telescopes, like the James Webb Space Telescope, is tasked with peering across the interstellar void to analyze the light filtering through TRAPPIST-1e's air, searching for the telltale chemical fingerprints of water vapor, methane, or oxygen, the potential signs that we are not alone. Leaving the compact family of TRAPPIST-1 behind, our search takes us 500 light-years deeper into the cosmos, to a world that forever changed our perspective on what's possible. In 2014, NASA Kepler Space Telescope, a mission dedicated to finding other Earths, delivered a historic revelation: Kepler-186f. This wasn't just another exoplanet. It was the very first world we ever discovered that was both almost identical in size to Earth and nestled perfectly within its star's habitable zone. That moment was a paradigm shift, proving conclusively that planets like ours are not unique miracles but are, in fact, common throughout the galaxy. Kepler-186f orbits a red dwarf star, much like Proxima Centauri and TRAPPIST-1, a classification that is becoming a common theme in our hunt for life. Its year lasts about 130 Earth days, and it receives just 1/3 of the energy from its star that Earth gets from the Sun. This places it on the cooler, outer edge of the habitable zone, a position that some scientists liken to that of Mars in our own solar system. But unlike Mars, Kepler-186f is large enough to likely have held onto a life-sustaining atmosphere, and its rocky composition suggests a landscape that could be hauntingly familiar, with continents, mountains, and perhaps even basins that could cradle liquid water. The most captivating and challenging aspect of this world is its probable state of tidal locking. Like our moon to Earth, one side of Kepler-186f likely permanently faces its star, locked in endless, blinding daylight, while the opposite hemisphere is consigned to an infinite frozen night. This creates a world of dramatic extremes, but between them lies a region of perpetual twilight, a narrow band stretching across the planet where the star forever hangs low on the horizon. This terminator line could be the most likely place for life to gain a foothold. Here, temperatures might be just right for water to remain liquid. Imagine a landscape where the sun never rises and never sets, casting everything in an eternal, soft amber glow. Unique photosynthetic life, if it exists, might huddle in this golden belt, with vegetation that could appear black or gray to our eyes, evolved to absorb every possible photon from the faint red star. This isn't the vibrant, sun-drenched Earth we know. It's a world of subtle tones and profound quiet, a testament to life's potential to adapt to the most extraordinary of circumstances. While Kepler-186f offered a glimpse of an Earth-sized world, our next destination presents a vision of what Earth itself might one day become. Located 1,400 light-years away in the constellation Cygnus, Kepler-452b earned the poignant nickname Earth's cousin for a profoundly compelling reason. It orbits a star that is a virtual twin of our own Sun. This marked another historic first, the initial discovery of a near-Earth-sized planet residing in the habitable zone of a G-type, Sun-like star. After finding so many promising worlds around tiny, flaring red dwarfs, Kepler-452b felt like a homecoming, a glimpse of a familiar family dynamic playing out around a star we could almost recognize as our own. The similarities are genuinely breathtaking. This planet's year lasts 385 days, just 20 days longer than our own annual journey around the Sun. It has spent an estimated 6 billion years within its star's habitable zone. That's 1.5 billion years longer than Earth has enjoyed its own life-friendly position. This staggering amount of time is more than enough for life to have not only emerged but to have potentially evolved into complex, even intelligent forms. Imagine a world where biology has had an extra 1.5 billion years to experiment and diversify. The evolutionary possibilities there are truly mind-boggling. However, this cousin is built on a slightly grander scale. With a diameter about 60% larger than Earth's, Kepler-452b falls into the category of a super-Earth. This size difference has major implications. Its stronger gravity would likely result in a much thicker, more substantial atmosphere than our own, potentially creating a powerful greenhouse effect that could turn the surface into a scorching, Venus-like landscape. Yet, that same thick atmosphere could also be a superb shield against cosmic radiation and a fantastic medium for redistributing heat, creating a stable global climate. The increased mass also suggests a far more active and prolonged geological life. A larger planetary interior would stay hotter for longer, fueling vigorous volcanic activity and plate tectonics for billions of years. This ongoing geological churn is crucial for life as we know it, as it helps regulate atmospheric carbon dioxide and cycles essential nutrients through the environment, maintaining the planet's long-term habitability. Standing on the surface of Kepler-452b, a visitor would experience a profound sense of the familiar made strange. The star in the sky would look almost identical to our Sun, though slightly older and a touch brighter. The stronger gravity would make every movement feel heavier, and the sky above might glow with a different hue, filtered through an atmosphere rich with unknown gases. It is a world of both comforting parallels and exhilarating unknowns, a place that represents one of our most tantalizing possibilities for finding a biosphere that has matured over an almost unimaginable span of deep time. Our journey now takes us 49 light-years away to a red dwarf star in the constellation Cetus, where a truly colossal world promises to rewrite the rules of habitability. LHS 1140b isn't just another exoplanet. It's a super-Earth of such immense proportions that it forces us to reconsider what a life-bearing world might actually look like. With a mass nearly 6 times that of our own planet and a diameter about 20% larger, this is a rocky behemoth, a terrestrial world on a scale we simply don't have in our own solar system. Its sheer bulk is its greatest asset in the search for life, as its powerful gravity is almost certainly strong enough to have captured and held onto a dense, substantial atmosphere, a critical shield against the radiation from its active red dwarf sun and a potential blanket to nurture a stable climate. This giant doesn't just have the right build, it has the perfect location. It orbits squarely within its star's habitable zone, but its path is far more leisurely than those of the tidally locked worlds we've encountered so far. A single year on LHS 1140b lasts a much more sedate 25 Earth days. This slower orbit, combined with the gravitational influence of a second outer planet in the system, might have prevented it from becoming fully tidally locked. Instead, it could be rotating slowly, offering a day-night cycle that could help distribute heat more evenly across its surface and prevent the kind of extreme temperature divides we see on other worlds. But the most breathtaking revelation about this planet comes from recent data gathered by the James Webb Space Telescope. Early analysis of starlight filtering through its atmosphere suggests a stunning, almost poetic possibility. LHS 1140b might not be a globe of uniform rock but a giant eyeball planet. In this mesmerizing scenario, the planet's day side, warmed by its faint star, hosts a vast, single, liquid water ocean. This wouldn't be a planet of scattered seas and continents, but a world dominated by one enormous, planet-wide sea, possibly thousands of kilometers across and surrounded by a ring of ice that transitions to the frozen solidness of the night side. This stable, temperate ocean, protected by a thick atmosphere and nurtured for billions of years, could represent one of the most promising environments for life we have ever identified beyond our solar system. It's a vision of a world both utterly alien and profoundly hopeful, a tranquil aquatic jewel shining in the void. Venturing just 31 light-years from Earth, we find a world that perfectly embodies the thrilling ambiguity at the heart of the search for alien life. GJ357d is a classic super-Earth, a planetary category that sounds deceptively familiar but often describes worlds that are anything but orbiting a small, quiet M-type dwarf star in the constellation Hydra. This planet is a heavyweight, possessing a mass roughly 6 times that of our own world. Its immense gravitational pull is the key to its enduring mystery, as it could have easily captured and held onto a massive, dense atmosphere for billions of years, creating an environment that is either a potential paradise or an utterly uninhabitable pressure cooker. What makes this distant world so compelling is its orbital position. GJ357d resides on the colder, outer fringe of its star's habitable zone. Its year is a long, slow 55.7 Earth days, and it receives only about as much stellar energy as Mars does in our own solar system. At first glance, that might sound disappointingly frigid. However, this is where that powerful gravity and potential atmosphere come into play. If GJ357d has managed to retain a thick, insulating atmosphere rich in hydrogen or other greenhouse gases, that gaseous blanket could perform a remarkable act of planetary climate control. It would effectively trap what meager heat it receives from its faint sun, redistributing warmth across the globe and potentially raising surface temperatures to a point where liquid water could flow freely. In this scenario, GJ357d could be a vast global ocean world, a dark water planet where life might swim in deep, sunless seas, warmed from within by geothermal vents or by the sheer pressure of its own immense atmosphere. But there is another, equally plausible possibility that highlights the challenge of interpreting data from so far away. With its significant mass, GJ357d might not be a rocky super-Earth at all. Instead, it could be what astronomers call a mini-Neptune. This would mean it lacks a solid surface entirely, comprised instead of a rocky core enveloped by a deep, suffocatingly dense atmosphere of hydrogen and helium, perhaps with a layer of supercritical water or high-pressure ices beneath. On such a world, the incredible atmospheric pressure and lack of a definable surface would preclude life as we know it. This fundamental duality, water world or gaseous dwarf, is what makes it such a high-priority target for the next generation of telescopes. The James Webb Space Telescope is poised to turn its powerful gaze towards this system, aiming to dissect the light filtering through GJ357d's atmosphere if it exists. By analyzing the chemical signatures in that light, scientists hope to finally answer the question: does this distant world hold a global, life-giving ocean, or is it a beautiful, barren giant, reminding us that the universe is full of both wonder and profound mystery? Now we arrive at one of the most intriguing and controversial worlds on our list, a planet that has single-handedly created a whole new category of potential habitability. 124 light-years away in the constellation Leo, orbiting a cool dwarf star, K2-18b is not a super-Earth. It's something entirely different and, until recently, something we had largely written off in the search for life, a mini-Neptune. This is a subclass of planet that is larger than Earth but smaller than Neptune, worlds thought to be not terrestrial at all, but rather gaseous with thick, crushing atmospheres and no solid surface to speak of. For years, we assumed such planets were hopelessly inhospitable. K2-18b shattered that assumption and forced us to dream bigger. The revelation began with data from the Hubble Space Telescope, which first suggested this world might have a significant amount of water vapor in its atmosphere. But the true revolution came with the launch of the James Webb Space Telescope. When JWST turned its unprecedented infrared gaze towards K2-18b, it didn't just confirm water, it painted a stunningly complex chemical portrait of a distant sky. The telescope's exquisite instruments detected the clear presence of methane and carbon dioxide in the planet's atmosphere. On its own, this is a monumental discovery. Finding carbon-bearing molecules, the fundamental building blocks of life as we know it, on a habitable zone world is a giant leap forward. It tells us that the basic chemical preconditions for life can exist on planets utterly unlike our own. But the most electrifying part of the discovery, the finding that sent a ripple of excitement through the global scientific community, was a tentative, fragile signal that hinted at something far more extraordinary. The data suggested the possible presence of another molecule, dimethyl sulfide or DMS. Here on Earth, dimethyl sulfide is a gas that has only one known significant source, biological activity. It is produced in vast quantities by marine phytoplankton, tiny organisms that form the base of the ocean's food web. To find it in the atmosphere of another world would be, quite simply, the most compelling potential indicator of life we have ever encountered. It is absolutely crucial to emphasize the word potential. The detection of dimethyl sulfide on K2-18b is not yet confirmed. The signal is weak, and scientists are tirelessly working to rule out other explanations or observational errors. The immense distance makes certainty incredibly difficult, yet this tantalizing hint is the reason K2-18b has become the poster child for a new and thrilling concept, the Hycean world. This term, a blend of hydrogen and ocean, describes a theoretical class of planet with a hydrogen-rich atmosphere covering a vast global liquid water ocean. On such a world, life wouldn't need a rocky beach to emerge. It could potentially flourish entirely within a planet-wide sea, hidden beneath a thick, gaseous sky. K2-18b, with its hints of water vapor and now these carbon molecules, fits this speculative profile perfectly. It presents a vision of life not on a familiar continent, but in an alien abyss, a boundless ocean under a permanent, pressurized haze, a biological realm completely divorced from the world of sun and soil that we call home. Leaving behind the gaseous mysteries of Hycean worlds, our search brings us to a system that offers something far more tangible and reassuring: stability. 100 light-years away in the constellation Dorado, the star TOI 700 stands out from the often tempestuous crowd of red dwarfs. While it shares the classification of an M-dwarf, it possesses a remarkably serene and quiet nature, making its planetary system a haven of cosmic calm. And orbiting this placid star is TOI 700d, an Earth-sized world that has quickly become one of the most promising and deeply studied candidates for habitability in the entire exoplanet catalogue. The discovery of this system is a triumph for NASA, a transiting exoplanet survey satellite, or TESS. Unlike the Kepler mission, which stared deeply at one patch of sky, TESS is designed to scan almost the entire heavens, methodically searching for the telltale dips in starlight that occur when a planet passes in front of its host star. TOI 700d was one of TESS' earliest and most exciting finds, a rocky world almost exactly the same size as Earth, located perfectly within its star's habitable zone. This planet completes a full orbit every 37 Earth days, a rhythmic and predictable dance that places it in that cherished Goldilocks region where temperatures could allow for liquid water to exist on its surface. What truly sets TOI 700d apart from many of its peers is the character of its sun. Most M-dwarf stars are notoriously volatile, prone to violent superflares that erupt with enough ferocity to strip away planetary atmospheres and sterilize surfaces with intense ultraviolet radiation. Proxima Centauri and TRAPPIST-1 are perfect examples of this stellar tantrum throwing. TOI 700, by beautiful contrast, is a picture of stellar tranquility. Observations over multiple years have shown it to be an exceptionally stable and quiet star, with no detected flaring activity whatsoever. This changes the entire equation for its planets. Instead of struggling to survive a relentless bombardment, TOI 700d has likely enjoyed billions of years of peaceful, constant sunshine. This stability is a gift of time, a time for an atmosphere to form and persist, for chemical reactions to simmer, and for the delicate, nascent steps of life to begin without the constant threat of apocalyptic stellar fury. Of course, this world is not without its own cosmic quirks. Given its close orbit around a small star, it is almost certainly tidally locked, with one hemisphere permanently bathed in daylight and the other shrouded in endless night. But with a stable star and the potential for a robust atmosphere, this locking might not be the death sentence for habitability it was once thought to be. Sophisticated climate models suggest that if TOI 700d has a substantial atmosphere, winds and ocean currents could effectively transport heat from the scorching day side to the freezing night side, potentially creating a wide, temperate band along the terminator line where conditions are just right. Some models even suggest the entire day side could be covered by a vast ocean, its clouds constantly reflecting the gentle, reddish light of its sun, while the night side might be encased in a thick, icy shell, with the meeting point between them a region of slushy sea ice and incredible biological potential. It's a world that presents a compelling argument for patience and peace, a testament to the idea that the most promising cradles for life might not be the most dramatic but the most consistent. Yet another red dwarf star holds a planetary prize, but this one comes with a celestial spectacle unlike any other. Just 24 light-years from Earth, in the constellation Scorpius, the star J667c is part of an extraordinary triple-star system. And orbiting this star is GJ 667cc, a super-Earth that offers a stark lesson in how our preconceptions can blind us to discovery. This world was actually hidden in plain sight within existing astronomical data, initially dismissed as mere noise because its signal didn't fit our expectations of what a planetary system should look like. It was only upon a second, more daring look that researchers confirmed its existence, a reminder that the universe often saves its greatest wonders for those willing to question their assumptions. GJ 667cc is a substantial world with a mass estimated to be at least 3.8 times that of Earth. This places it firmly in the super-Earth category, suggesting a rocky planet with a solid surface, though one where the gravity would feel significantly stronger underfoot. Its orbit is a swift 28-day journey around its parent star, a path that nevertheless places it squarely within the star's habitable zone. The reason a planet so close to its star can be temperate lies in the nature of the star itself. GJ 667c is a faint red dwarf, so its habitable zone is drawn in very tight. The planet receives slightly less light from its star than Earth does from the Sun, but astronomers believe its potential atmosphere could easily trap enough of that energy to create comfortable, Earth-like surface temperatures. But the true marvel of this world is not found on its surface but in its sky. GJ 667c is gravitationally bound to two other stars, GJ 667a and b, which are themselves a closely orbiting pair of K-type orange dwarfs. From the perspective of an observer on GJ 667cc, this creates a panorama of almost mythic proportions. Its parent star, the red dwarf, would hang in the sky as a large, dim, reddish orb. The two companion stars, however, would appear together in the distance as brilliantly luminous points of light, shining with a combined intensity far greater than our full moon. They would be close enough to be visibly distinct, a dazzling double star that would be constantly visible both day and night, casting faint, ever-shifting shadows. There would be no true darkness on this world, only a perpetual, soft glow from this celestial duo. This complex light environment would force any potential life to adapt in extraordinary ways. Photosynthetic organisms would have to evolve to harness energy from three different light sources, each with its own unique color spectrum: the deep red of the primary star and the brighter, whiter light of the distant twins. The circadian rhythms of animals and plants would be untethered from a simple day-night cycle, instead governed by a more intricate dance of light intensities and colors. It's a world where the very concept of a day is blurred, a place bathed in an eternal, multi-hued twilight that challenges our Earth-centric imagination and opens up breathtaking possibilities for how biology might flourish under three suns. In the constant flow of new planetary discoveries, some worlds immediately capture the attention of the scientific community, not just for what they are, but for what they are not. A mere 31 light-years from Earth, orbiting a star in the constellation Cygnus, Wolf 1069b is one such world, a study in promising serenity. Discovered in 2023 by a team using the Carmenes instrument in Spain, this exoplanet represents a rare and precious find, an Earth-mass planet, almost exactly the same size as our own world, positioned flawlessly in the center of its star's habitable zone. The statistics alone are compelling. It completes a full orbit around its dim red dwarf host in just over 15 Earth days, a rapid year that is nonetheless perfectly timed to keep it within that stellar sweet spot. The amount of energy it receives from its star is about 65% of what Earth gets from the Sun, a level that on its own would suggest a chilly, Mars-like environment. However, this is where the planet's other attributes come into play. Its Earth-like mass means it almost certainly has a rocky composition, and its gravity is strong enough to have likely held onto a substantial atmosphere over billions of years. This potential atmosphere is the key that could unlock its habitability, A blanket of gases rich in greenhouse molecules like carbon dioxide could effectively trap that incoming stellar heat, raising global temperatures to a point where water wouldn't just freeze or evaporate, but could persist as a liquid on the surface. But the true star of this story isn't just the planet, it's the sun it orbits. Wolf 1069 is a remarkably quiet and inactive red dwarf. This single characteristic elevates this world from simply intriguing to one of the most promising targets we know of. As we've seen with Proxima Centauri and TRAPPIST-1, the violent, flaring tantrums of active M-dwarfs can bombard their planets with life-sterilizing radiation and strip away their atmospheres, effectively dooming any chance for biology to arise. Wolf 1069 shows no such activity. It is a calm, stable, and gentle star, offering its planetary companion a consistent and non-lethal flow of energy. This profound stellar tranquility means that if Wolf 1069b did form a thick atmosphere early in its history, it almost certainly still has it. This combination of factors, an Earth-sized planet, a central habitable zone orbit, and a quiet star, is the holy grail for astronomers. It makes this world one of the top candidates in the entire sky for possessing surface conditions that could be conducive to life. Given its likely tidal locking, the most plausible scenario for Wolf 1069b is that of an eyeball planet. On its permanent dayside, under the constant glow of its reddish sun, a vast circular ocean of liquid water could exist. This ocean would be surrounded by a ring of ice that gradually thickens towards the terminator line, eventually giving way to the global glacier of the eternal night side. The most habitable region would be that slushy, dynamic boundary between light and dark, where liquid water, ice, and atmosphere all meet. The next great leap in understanding this world will come from the James Webb Space Telescope and other future observatories. They will attempt to capture the light filtering through its atmosphere, searching for the chemical fingerprints of water vapor, carbon dioxide, and perhaps even methane or oxygen. The telltale signs that this serene world is not just another rock in space, but a living, breathing oasis. Long before we were marveling at the intricate systems of TRAPPIST-1 or the tranquil promise of Wolf 1069, there was a discovery that felt like a revolution in real time. In 2011, the Kepler Space Telescope team announced a world that captured the global imagination and fundamentally shifted the public's perception of our place in the universe, K2-18b. Located 600 light-years away in the constellation Cygnus, this planet wasn't just another data point, it was a symbol of hope and a monumental first. It was the very first planet discovered by the Kepler mission to orbit comfortably within the habitable zone of a star that is a close cousin to our own Sun, a G-type dwarf. This wasn't a world tethered to a flaring red dwarf. This was a planet in a family photo we recognized, offering a vision of habitability that felt directly comparable to our own home. The numbers associated with K2-18b are strikingly familiar, yet beautifully alien. Its year lasts 290 Earth days, a stately and slow orbital waltz that is remarkably similar to our own 265-day journey. Its orbital distance is about 85% of Earth's, but because its star is slightly smaller and cooler than the Sun, this still places it perfectly in that liquid water-friendly zone. From the surface, the star would appear almost identical to our Sun in color and size, hanging in an alien sky and bathing the landscape in a light that would feel profoundly familiar to a human eye. This combination of a Sun-like star and an Earth-like year created an immediate and powerful connection, making it easier than ever before for people to picture another living world. However, the true nature of K2-18b remains one of the most enduring mysteries of early exoplanet science, a perfect example of the super-Earth problem. With a radius about 2.4 times that of Earth, this planet exists in a frustrating and poorly understood size category. Is it a terrestrial world, a massive rocky planet often called a mega-Earth? If so, its surface gravity would be crushing, perhaps 2 to 3 times stronger than what we experience. Such an environment would create a profoundly different world. Mountains would be lower and wider. Any atmosphere would be incredibly dense and pressurized, and the very geology would be dominated by unimaginably powerful tectonic forces. Life, if it could exist at all, would likely be flat, sturdy, and built to withstand immense pressure. The other, perhaps more likely possibility, is that Kepler-22b is not a rocky super-Earth at all, but a mini-Neptune. This would mean it possesses a relatively small rocky core, but that core is engulfed by an enormously deep and dense atmosphere of hydrogen and helium, thousands of miles thick. There would be no solid surface to speak of. Instead, the atmosphere would gradually get thicker and hotter with depth until it reached a state of supercritical fluid, a bizarre form of matter that is neither liquid nor gas. In such an environment, the concept of an ocean or a continent is meaningless. The pressures at depth would be so astronomical that they would crush any complex chemistry necessary for life as we define it. This fundamental ambiguity is what makes Kepler-22b so fascinating. It is either a planet of incredible, solid substance or a world of beautiful, uninhabitable gas, and we still lack the observational power to know for sure. Its legacy is secure not as a confirmed abode for life, but as the trailblazer that first showed us the incredible diversity of worlds waiting in the habitable zones of sun-like stars, a promise of wonders yet to be fully understood. As we venture closer to our own cosmic neighborhood, a mere 12 light-years from Earth, we encounter a star so faint it wasn't even discovered until 2003. Teegardens star is an ancient red dwarf, a relic from the early universe that is believed to be at least 8 billion years old, nearly twice the age of our own Sun. And orbiting this diminutive, time-worn star is one of the most tantalizing worlds we know, Teegardens Star B. This planet is a remarkable find with a mass almost identical to that of Earth, placing it in that elite category of truly Earth-sized worlds. Its orbit is extraordinarily short, a mere 4.9 Earth days, yet this rapid journey still places it squarely within its star's habitable zone. This intimate distance is necessary because Teegardens star is so cool and dim. To receive enough warmth for liquid water, a planet must huddle very close indeed. This proximity almost certainly means the planet is tidally locked, presenting the now familiar scenario of a permanent day side and a perpetual night side. However, the context here is utterly different because of the star's mind-boggling age. This system has existed in a state of profound stability for billions of years, longer than our solar system has even been alive. Imagine the implications of that vast stretch of time. If Teegardens Star B did possess the right ingredients, a substantial atmosphere and liquid water, it has had an almost unimaginable head start on the journey of life. While Earth's biosphere has had roughly 4 billion years to evolve from single-celled organisms to the complexity we see today, any life on this ancient world would have had potentially twice that long or more to develop and diversify. This abundance of time is the most captivating and humbling aspect of this world. It forces us to confront possibilities that stretch far beyond our own planetary experience. What does biology become with 8, 10, or 12 billion years to evolve? On Earth, we see intelligence and technological civilization appear only in the very last sliver of our planet's history. On a world as ancient as Teegardens Star B, intelligence may have arisen, flourished, and perhaps even transcended its biological origins eons before the first microbes even appeared in Earth's primordial oceans. The potential for a civilization to achieve a level of advancement that is utterly incomprehensible to us is not just possible. It could be the natural outcome of such an immense timeline. The planet's surface, if life took hold, might be a testament to eons of uninterrupted evolution, a landscape so thoroughly managed and integrated with biology that it appears as a single planet-wide sentient organism. Yet this thrilling possibility is balanced against the harsh realities of a red dwarf system. The star's extreme age, while offering time, also presents a challenge. Over such cosmic epochs, a star gradually burns through its hydrogen fuel and grows brighter. Billions of years ago, K2-18's star would have been even cooler and dimmer than it is today. This means the habitable zone has been slowly migrating inward over the eons. K2-18's star B may have started its life as a frozen ice ball far outside the zone, only being warmed into potential habitability within the last few billion years as its star evolved. The question, then, is whether this world was a late bloomer, its oceans melting and its atmosphere thawing just in time for life to get a later start, or if it has been a continuously habitable oasis for the majority of the universe's existence, a rare and stable cradle in a changing cosmos. Sometimes the most extraordinary discoveries are not made by looking out into the void, but by looking back with fresh eyes at data we thought we had already mastered. That is precisely the story of our next world, a planet that was hiding in plain sight. In 2020, astronomers reanalyzing old observations from the now retired Kepler Space Telescope found a signal everyone else had missed. Buried within the noise was Kepler 1649c, a planet that instantly shot to the top of the list of the most Earth-like worlds we have ever found, a true Goldilocks planet in every sense of the term. Located 300 light-years away in the constellation Cygnus, this world orbits a faint red dwarf star, but what sets it apart is its stunning combination of characteristics, a pairing so familiar it feels almost like looking in a mirror. First, its size. Kepler 1649c is just 1.06 times the radius of Earth. This is as close to a perfect Earth twin in terms of physical dimensions as we have ever discovered, making it almost certain to be a rocky world with a solid surface. Second, and perhaps even more importantly, is its stellar diet. The amount of light and heat this planet receives from its sun is calculated to be about 75% of the energy Earth gets from our sun. This places it firmly and unambiguously in the very heart of its star's habitable zone. Not on the chilly outer edge, not on the scorching inner boundary, but right in the comfortable middle where conditions for liquid water are most promising. This combination is incredibly rare. We have found planets that are Earth-sized, and we have found planets that get Earth-like amounts of starlight, but finding both qualities in a single world is the jackpot. It suggests a planet where the gravity would feel familiar, where the landscape might look recognizable, and where the temperature, assuming it has a similar atmosphere to Earth's, could be remarkably temperate. A visitor might stand on a surface of rock and soil, looking up at a sun that appears larger in the sky than our own but glows with a dim, deep crimson light. The sheer statistical unlikelihood of finding a world that matches these two key metrics so precisely makes astronomers confident that planets like this are probably common throughout the galaxy, a thrilling implication for the universe's potential to be filled with life. Of course, this promising picture is painted on a familiar red dwarf canvas, which means it comes with its own set of challenges. The planet is tidally locked to its star, and its year is incredibly short, a mere 19.5 Earth days. Its star is also known to be flare-active, which could pose a threat to any atmosphere. Yet, the very fact that it checks the two most important boxes, size and energy, so perfectly makes it one of the most important objects of study we have. It is a benchmark, a Rosetta Stone for understanding what a truly Earth-like planet might look like around the most common type of star in the Milky Way. Kepler 1649c is a testament to perseverance and the power of second looks, a hidden gem that reminds us that even in our own archival data, we might still find a world that feels like home. Journeying just 12 light-years from Earth, we arrive at a star so faint and inconspicuous it was only discovered at the very end of the 20th century. GJ 1061 is a quiet, unassuming red dwarf, but it holds a secret that makes it incredibly special. It is the closest single red dwarf to our solar system known to host not just one but multiple planets. And of this compact family, one world in particular presents astronomers with a beautifully complex puzzle. GJ-1061c is a planet of profound duality, a world that sits right on the knife's edge between a scorching wasteland and a temperate oasis, forcing us to ask one of the most fundamental questions in planetary science: what separates a living world like Earth from a dead one like Venus? This planet's credentials are immediately impressive. Its mass is calculated to be about 1.7 times that of Earth, placing it squarely in the category of a super-Earth and all but guaranteeing it has a rocky, solid surface. Its orbit is a rapid 6.7 Earth days, a dizzyingly short year that is nonetheless long enough to position it tantalizingly close to the inner boundary of its star's habitable zone. This location is the source of both its great promise and its deep uncertainty. GJ-1061c receives about 40% more stellar radiation than Earth does from the Sun. At first glance, that number might sound alarmingly high, pushing it into a potentially runaway greenhouse state where any oceans would long since have boiled away into space. This is the Venus scenario, a fate where the planet's proximity to its star seals its destiny as a hellish, high-pressure inferno. However, the universe is rarely so simple, and this is where the fascinating debate begins. The star this planet orbits is not our Sun. It is a much cooler, dimmer red dwarf. This means the nature of its light is different, with a higher proportion of energy in the infrared part of the spectrum. Some climate models suggest that an Earth-like atmosphere might actually be quite effective at reflecting or managing this type of heat, potentially preventing the catastrophic warming we initially fear. The wild card, the factor that could tip the balance entirely, is the presence of clouds. On Earth, clouds play a critical role in regulating temperature by reflecting a significant amount of solar energy back into space. If GJ-1061c has developed a robust cloud cycle, those perpetual cloud decks could act as a brilliant planetary sunshade, bouncing a large portion of that incoming stellar energy away before it can ever heat the surface. In this optimistic scenario, the clouds would cool the planet just enough to keep it comfortably within the habitable zone, a temperate world with liquid water oceans and a stable climate. The character of its host star adds another layer of intrigue to this story. Unlike the volatile tantrums of Proxima Centauri, GJ-1061 is exceptionally quiet and magnetically inactive. It doesn't produce the massive superflares that can strip atmospheres and bombard surfaces with harmful radiation. This stellar serenity is a gift of time and stability. It means that if GJ-1061c ever did possess a substantial atmosphere and abundant water, it has almost certainly been able to hold onto them for billions of years undisturbed. This tranquility makes it one of the very best targets for future atmospheric study. The James Webb Space Telescope will be able to stare at this nearby, quiet system and analyze the light filtering through GJ-1061c's air if it exists. The chemical signatures it finds will finally settle the debate, revealing whether we are looking at a world with the thick, crushing CO2 atmosphere of a Venus twin, or one with the balanced, life-nurturing mix of gases that would mark it as one of the most Earth-like worlds we have ever found. While many of the worlds we've visited demand we stretch our imagination, our next destination offers a promise of something more tangible and immediately knowable, a world that feels almost within our grasp. Just 100 light-years away, orbiting a faint red dwarf star in the constellation Eridanus, LP 899c stands as a testament to the power of international collaboration and next-generation technology. You might also hear it called Speculus 2c, a name that hints at its deliciously sweet potential for discovery. This planet wasn't found by a single telescope, but by a powerful tag team of observatories working in concert, and their findings have catapulted this super-Earth to the very top of the list of places we need to search for signs of life. The discovery story itself is a marvel of modern astronomy. It began with NASA Transiting Exoplanet Survey Satellite, or TESS, which is designed to scan the sky for the telltale dimming of stars that suggests a planet is passing in front of them. TESS identified the inner world in this system, but it was a network of ground-based telescopes named the Speculoos Project, the search for habitable planets eclipsing ultra-Cool stars, that took a closer look. Speculoos, with its incredibly sensitive infrared eyes optimized for seeing the dimmest stars, not only confirmed the first planet but spotted a second, larger world that TESS had missed. This is LP-899c, a planet whose very discovery showcases how much more we can see when we combine the power of space-based and Earth-based astronomy. What makes this world so exceptionally promising isn't just its size, though that is a key part of the puzzle. It's about 40% larger than Earth, which firmly places it in the super-Earth category. This suggests a rocky world with a solid surface, but one with significantly stronger gravity. More importantly, its orbital path is a thing of beauty for astrobiologists. It takes about 8.4 Earth days to complete a journey around its cool, quiet star, a path that places it perfectly within the middle of the star's habitable zone. It receives just slightly more stellar energy than Earth does from our Sun, but because that energy comes from a much cooler star, the climate equations are different. Most models suggest that with a reasonably Earth-like atmosphere, the surface temperatures on LP-899c could be remarkably similar to our own planets. This combination of factors, its rocky composition, its ideal location in the habitable zone, and the serene nature of its host star, makes it perhaps the single best target in the entire sky for the James Webb Space Telescope to study. Its star is exceptionally quiet and inactive, meaning it doesn't produce the violent flares that can complicate atmospheric readings or threaten a planet's air. This stellar tranquility provides a crystal-clear backdrop against which JWST can perform its magic. The telescope will be able to watch as starlight filters through the atmosphere of LP-899c during its transits, dissecting that light into a spectrum that acts like a chemical barcode. Scientists will be searching for the telltale signs of water vapor, carbon dioxide, methane, and even oxygen, the potential biosignatures that could indicate a living world. The possibility of vast liquid water oceans here is not just speculative fantasy, it's a leading hypothesis. Given its size and position, LP-899c could very well be a water world, its entire surface a single, globe-spanning ocean deep enough to drown continents. If that's the case, the view from space would be a breathtaking, unbroken azure marble, dotted with swirling white clouds under the gentle glow of its deep red sun. The James Webb Space Telescope is our key to unlocking this mystery, and the data it gathers from this nearby, pristine system could provide us with the most convincing evidence yet that the galaxy is not only full of worlds, but full of worlds that are truly alive. Venturing 42 light-years from Earth, we find a stellar system that defies our expectations of planetary architecture and offers a glimpse into a different kind of solar family. The star HD 40307, slightly cooler and older than our Sun, is a K-type orange dwarf, a classification known for its stellar stability and longevity. For years, astronomers believed this star was home to just 3 planets, all orbiting far too close to be anything but scorched, barren worlds. But a revolutionary reanalysis of the data revealed something astonishing. This system actually contains not 3 but 6 planets, and the outermost member of this family is a world of profound significance. HD 40307G is a super-Earth that broke the mold, proving that complex multi-planet systems can and do have members orbiting in the life-giving habitable zone. This planet's journey around its star is a stately 200 Earth days, a rhythmic and slow dance that places it perfectly within that coveted region where temperatures could allow for liquid water to exist. From the surface, its sun would appear a deep, rich orange, casting a warmer, more golden light than our own sun's white-yellow glare. The sheer age of this system is a key part of its story. Its star is billions of years older than ours, meaning this planet has been sitting in this stable, life-friendly position for an almost incomprehensible span of cosmic time. If the ingredients for life were ever present, they have had an eternity to simmer, interact, and potentially blossom. However, life on this world would face a formidable challenge: gravity. HD 40307G is a true super-Earth in every sense of the word, with a mass nearly 7 times greater than our own planet's. This immense bulk would create a surface gravity roughly twice as strong as what we experience on Earth. Imagine a world where every movement is an effort, where your body would feel twice as heavy, and where simply walking would be a strenuous activity. The very landscape would be shaped by this force. Mountains would be lower and wider, unable to support tall, jagged peaks under their own immense weight. Any potential life forms would likely be stout, sturdy, and built low to the ground to withstand the constant, crushing pressure. This powerful gravity is also the planet's greatest asset in the quest for habitability. A world with such a strong pull is a master at holding onto its atmospheric possessions. It is almost certain to have captured and retained a tremendously thick, deep atmosphere. This dense shroud of gas would act as a superb blanket, efficiently distributing heat from the warm day side to the cooler night side, potentially creating a remarkably stable and temperate global climate despite any tidal locking. It would also provide a formidable shield against cosmic radiation and asteroid impacts. The potential views from the surface would be breathtaking. The sky might glow in unfamiliar hues, a deep purple or a constant, rich twilight orange filtered through an air thick with nitrogen, carbon dioxide, and perhaps even methane. While the conditions would be extreme by our standards, they are not a definitive barrier to life, but rather a blueprint for an entirely different kind of biology, one built for power and resilience on a grand, super-sized scale. While the worlds we've explored so far have shown us the incredible diversity of potential homes for life, our next destination offers something arguably even more valuable than size or spectacle: the promise of peace. A mere 11 light-years from Earth, in the constellation Virgo, orbits a planet that has become a favorite among exobiologists for one simple reason: its sun is a model of good behavior. Ross 128b is a temperate world circling a red dwarf star that stands in stark contrast to the violent tantrums of Proxima Centauri. This stellar serenity makes its potentially habitable planet one of the most compelling and stable environments we have yet discovered in our cosmic neighborhood. The planet itself is a substantial world with a mass calculated to be about 1.35 times that of Earth. This places it firmly in the super-Earth category, suggesting a rocky composition and a solid surface, albeit one where the gravity would feel noticeably stronger than what we are used to. Its orbit is incredibly short, a rapid 9.9 Earth days, but this breakneck year is necessary to keep it warm. Because its star is so small and cool, the habitable zone is drawn in very close. To receive enough stellar energy for liquid water, a planet must be practically hugging its sun. Ross 128b's tight orbit places it right in the heart of that zone, receiving only about 38% more radiation from its star than Earth gets from the sun. With a reasonably reflective atmosphere, this could easily translate into remarkably Earth-like surface temperatures. But the true star of this story, the factor that elevates Ross 128b from merely interesting to profoundly promising, is the character of its parent star, Ross 128. In the turbulent community of red dwarfs, this star is a renowned pacifist. Unlike Proxima Centauri, which frequently unleashes devastating superflares that bathe its planets in lethal X-ray and ultraviolet radiation, Ross 128 is remarkably quiet and magnetically inactive. It doesn't throw stellar fits. This profound tranquility is a game-changer for the potential development of life on its orbiting world. A calm star means that any atmosphere Ross 128b formed in its youth would not have been relentlessly stripped away over billions of years by stellar winds and radiation pressure. It means the planet's surface is not being regularly sterilized by ultraviolet flares, allowing delicate chemical reactions to proceed uninterrupted. It offers the most precious commodity life needs to get started: stability. Given its close orbit, Ross 128b is almost certainly tidally locked, with one hemisphere locked in permanent daylight and the other in endless night. Yet, with a thick atmosphere likely held in place by its gravity and protected by its star's calm nature, this locking might not be the obstacle to life it was once thought to be. Climate models suggest that atmospheric circulation could effectively ferry heat from the scorching day side to the frigid night side, potentially creating a wide, temperate band along the twilight terminator line where conditions are just right for liquid water to persist. This could manifest as an eyeball planet with a single, vast liquid water ocean on the day side surrounded by a ring of ice that gradually thickens into the global glacier of the night side. The most likely place for life to thrive would be in that dynamic boundary between the ocean and the ice, a slushy, nutrient-rich region constantly churned by atmospheric currents. For astronomers, Ross 128b represents a nearby laboratory for studying a potentially habitable world that hasn't been brutally punished by its star, offering one of our best chances to find a biosphere that has been allowed to evolve in peace for billions of years. Journeying 1,200 light-years from Earth, we arrive at a planetary system that feels both intimately familiar and profoundly alien. The star Kepler-62, a K-type orange dwarf slightly smaller and cooler than our Sun, is the anchor for a family of 5 known worlds. And the outermost member of this distant family is a world that holds a special place in the history of our search for life, Kepler-62f. When it was confirmed in 2013, this planet was one of the most Earth-like worlds we had ever found, a pioneering discovery that expanded our understanding of where life might take root. What makes Kepler-62f so compelling begins with its size. With a radius just 1.4 times that of Earth, it is almost certainly a rocky world, a terrestrial planet with a solid surface of stone and soil that a probe could one day land on. Its orbit is a stately 267 Earth days, a rhythmic journey that places it perfectly within the habitable zone of its orange sun. This orbital real estate is particularly promising because it's on the cooler outer edge of that zone. The planet receives only about 41% of the stellar energy that Earth gets from our Sun, a level comparable to what Mars receives in our own solar system. But unlike Mars, which is too small to hold onto a substantial atmosphere, Kepler-62f's larger size and stronger gravity make it an excellent candidate for retaining a thick, life-nurturing blanket of air. This potential atmosphere is the key to unlocking the planet's climate and is the source of some of the most fascinating speculation about this world. With a thick enough atmosphere rich in greenhouse gases like carbon dioxide or methane, Kepler-62f could effectively trap what meager heat it receives, creating a powerful greenhouse effect that would warm the surface well above what its distant orbital position might suggest. In this scenario, it could be a world of surprising temperate conditions, perhaps even hosting a global ocean beneath a hazy, orange-tinged sky. Its long year would create seasons that unfold with a slow, majestic pace, each lasting for months on end. The axial tilt of the planet, a factor we cannot yet measure, would further dictate the intensity of these seasons. A significant tilt could mean dramatic shifts between long, dark winters and brief, lush summers, while a minimal tilt would result in a much more uniform and stable climate across the globe. The view from the surface would be unlike anything on Earth. Its sun, an orange dwarf, would appear larger in the sky than our sun, but would glow with a deep, warm, amber light, casting long shadows and bathing the landscape in a perpetual golden hour hue. If it has liquid water oceans, they would shimmer with a coppery sheen. The possibilities for life are as vast as the world itself. If its oceans are real, they could be home to entirely unknown aquatic ecosystems, perhaps based on exotic biochemistries adapted to the lower light levels. The plant life, if it exists, might not be green. Vegetation here could evolve to appear black or deep purple to most efficiently absorb every precious photon of that orange light. Kepler-62f stands as a testament to the idea that a planet doesn't need to be a perfect twin of Earth to be a viable home for life. It simply needs the right combination of geology, atmosphere, and stellar energy to write its own unique biological story. Just 12 light-years from Earth, a star shines in the constellation Cetus that has been a fixture in both science and science fiction for generations. Tau Ceti is a G-type yellow dwarf, a near twin to our own Sun in both size and luminosity, making it one of the very closest solar analogues to our own. For decades, we've wondered if this familiar star might host planets of its own, and we now know it does, a system of at least 4 worlds, one of which presents us with a fascinating and heated debate about the very nature of habitability. Tau Ceti e is a super-Earth that orbits terrifyingly close to its star, a mere 20% of the distance between Earth and the Sun. This blisteringly fast orbit gives it a year that lasts just 168 Earth days, a journey that places it squarely on the searing inner edge and perhaps even just outside of the star's calculated habitable zone. The sheer energy this planet receives makes it a prime candidate for a runaway greenhouse effect, a climatic apocalypse where the oceans boil away and the surface transforms into a scorching hellscape. Scientists estimate its surface temperature, without the mitigating effects of an atmosphere, could soar to around 250 degrees Celsius, far too hot for liquid water to exist. With a mass nearly 4 times that of Earth, its powerful gravity would almost certainly have pulled down a massive, dense atmosphere, but this could be its curse rather than its salvation. A thick shroud of gases like carbon dioxide would trap incredible amounts of heat, creating a crushing, superheated environment more extreme than even Venus, effectively baking the planet and eliminating any chance for life as we know it. This would be a cautionary tale, a vision of what Earth's future could hold if our own climate spirals out of control, showing us the devastating end result of a planet that gets just a little too close to its sun's furnace. Yet, the story of Tau Ceti e is far from simple, because this system threw astronomers a curveball that continues to spark controversy and hope. Several years ago, analysis of the starlight from Tau Ceti revealed tentative, incredibly faint spectral signals that hinted at the presence of specific molecules in the system's debris disk. The readings suggested the possible existence of oxygen, carbon monoxide, and cyanogen, a collection of chemicals that, in the right context, could be interpreted as potential biomarkers, indirect signs of biological activity. It is absolutely critical to understand that these detections were highly disputed within the scientific community. The signals were at the very edge of what our instruments could detect, and many astronomers attribute them to noise, data processing artifacts, or other non-planetary sources. They are not confirmed, and most regard them with extreme skepticism. But the mere possibility, however slim, forces us to confront an electrifying question. If these signals were real and somehow linked to Tau Ceti e, how could life exist on such an infernal world? The answer might lie in the concept of a habitable atmosphere rather than a habitable zone. It's a radical idea that suggests a planet's potential for life isn't dictated solely by its distance from its star, but by the unique composition and structure of its air. Perhaps Tau Ceti e possesses an atmosphere so extraordinarily reflective, with such brilliantly high cloud cover, that it acts as a planetary-scale sunshade, bouncing a vast amount of stellar radiation back into space before it can heat the surface. Alternatively, its atmosphere could be dominated by molecules we rarely consider, gases that are efficient at blocking specific wavelengths of light while allowing just enough warmth through to maintain an equilibrium. It's a long shot, a scenario that defies our current climate models, but it's a powerful reminder that the universe is under no obligation to follow our terrestrial rulebook. Tau Ceti E stands as a monument to scientific controversy, a world that is almost certainly a dead Venus-like furnace, but one that, just maybe, could be teaching us that life finds a way in the most unexpected of places. Leaving behind the sun like stars and their tantalizing controversies, we plunge into the atmosphere of a world that defies every conventional image we hold of a planet. Just 48 light-years away in the constellation Ophiuchus, K2-18b is not a super-Earth, and it's certainly not a terrestrial twin. This world is a mini-Neptune, a class of planet that for years was dismissed as a gas-shrouded dead end in the search for life. But K2-18b is the world that forced us to completely rethink that assumption, becoming the prototype for a revolutionary and thrilling new concept, the Hycean world. From the outside, this planet appears utterly inhospitable. It's a swollen globe about 2.7 times the size of Earth, but with a mass nearly 7 times greater. This low density tells us it isn't made of rock and metal alone. It's a world dominated by an atmosphere, a deep and crushing shroud of gas. The surface temperature soars to over 500 degrees Fahrenheit, and the atmospheric pressure is unimaginable, thousands of times greater than what we experience at sea level. It orbits its dim red dwarf star in a blistering 38-hour year, so close that it's perpetually baked. If you were to descend into this atmosphere, you would encounter a thick, perpetual fog, a global haze that blocks our view of whatever lies beneath. For a long time, that was the end of the story, a fascinating but hopelessly uninhabitable world. But then, a radical idea began to take hold. What if this steamy, high-pressure atmosphere isn't the end of the planet, but merely its sky? What if, beneath this impenetrable global haze, there exists a boundary, a point where the incredible pressure transforms the gases into something else entirely? This is the core of the Hycean world hypothesis. Scientists now believe that on a planet like K2-18b, the atmosphere might not be a bottomless abyss of gas. Instead, at a certain depth, the pressure becomes so immense that the hydrogen-rich air undergoes a phase change, gradually giving way to a global, planet-wide ocean. This wouldn't be an ocean like those on Earth, resting on a rocky seabed. This would be an ocean without a bottom, a vast, deep expanse of water that extends thousands of miles down toward a hot, rocky core, its surface perpetually hidden from view by the opaque, soupy atmosphere above. In this astonishing scenario, the concept of a surface becomes meaningless. The entire planet is effectively a single, enormous ocean. Its top layer a supercritical fluid where the distinction between liquid and gas blurs, transitioning into liquid water under mind-boggling pressure. And it is in this sunless, abyssal ocean that the potential for life emerges, completely shielded from the harmful radiation of its star by miles of atmosphere and water, and potentially warmed from below by the heat of the planet's core through geothermal vents. This environment could be remarkably stable. The chemistry for life could be rich, with nutrients churned up from the depths. We know from Earth that life thrives in the most extreme places, clustering around hydrothermal vents on our own dark ocean floors, entirely independent of sunlight. On K2-18b, an entire biosphere could exist in perpetual darkness, a realm of bizarre organisms living under pressures that would instantly crush any earthly creature, perhaps communicating through bioluminescence in the eternal blackness. This world forces us to abandon our Earth-centric search for land and shorelines, and to instead imagine life flourishing in a boundless, pressurized sea, proving that the habitable zone isn't just a region around a star, it can be a state of matter hidden deep within a planet. But as our journey through the catalogue of distant exoplanets draws to a close, we arrive at a profound realization that shakes the very foundation of our search. For decades, we've been trained to look for other Earths, planets circling stars in that perfect, life-giving zone. Yet some of the most promising worlds for hosting alien life aren't planets at all, and they aren't light years away. They are right here in our own celestial backyard, orbiting the giant planets of our solar system. These icy moons, once thought to be frozen, dead rocks, are now recognized as dynamic ocean worlds, expanding our definition of habitable in ways we never imagined. First among these incredible moons is Jupiter's enigmatic Europa. From the outside, it appears as a cracked, white billiard ball, a world sheathed in an ice shell perhaps 10 to 15 miles thick. But beneath that frozen crust lies the single largest ocean in our entire solar system, a body of liquid water, so vast it contains more than twice the volume of all Earth's oceans combined. This isn't a dark, stagnant sea. The immense gravitational pull from Jupiter constantly squeezes and flexes the moon's interior, generating tremendous heat through a process called tidal heating. This internal furnace is likely keeping that global ocean liquid and could be powering hydrothermal vents on the seafloor, spewing mineral-rich, superheated water into the abyss. On Earth, such vents are oases of life, supporting entire ecosystems that thrive in complete darkness, independent of the sun's energy. The possibility that similar communities of exotic alien organisms could be thriving right now in Europa's deep, dark ocean is one of the most compelling reasons we have to send a mission there. Next, we turn to Saturn's brilliant white moon, Enceladus. This small world, only 300 miles across, delivered one of the most stunning revelations in planetary science. The Cassini spacecraft didn't just photograph this moon. It flew directly through giant plumes of water vapor and ice that were erupting from a subsurface ocean, shooting hundreds of miles into space from fractures near its south pole. Cassini's instruments tasted these plumes and found they were not just water. They were a complex cocktail containing salts, silica nanoparticles suggestive of hydrothermal activity, and most importantly, a variety of organic molecules, the carbon-based building blocks of life. Enceladus presented us with a free sample of its inner ocean, delivered straight to our spacecraft, and it told us that this tiny moon has all the key ingredients for life: water, chemistry, and a source of energy. It is a world that has practically begged us to come back with a dedicated mission to search for life within its jets. Then there is Titan, Saturn's largest moon, and a world so bizarre it feels like a universe unto itself. This is the only moon in our solar system with a thick, substantial atmosphere, a hazy orange shroud that hides its surface from visible light. But when we pierced that haze with radar and infrared cameras, we found a landscape that is both eerily familiar and utterly alien. Titan has rivers, lakes, and seas, but they are not filled with water. On its frigid surface, at -290°F, water is as hard as rock. Instead, the role of water is played by liquid methane and ethane. This is a hydrocarbon world where it rains methane, carves methane rivers, and fills methane lakes. Yet, beneath this bizarre, frozen surface, scientists strongly suspect Titan also hides a global subsurface ocean of liquid water, much like Europa and Enceladus. This means Titan offers two separate and potential arenas for life: a familiar water-based ocean deep underground, and on its surface, the potential for a truly alien form of life, a biology that uses liquid methane instead of water as its solvent. It is a world that challenges every assumption we have about what life requires. Our own Jupiter commands yet another oceanic moon, the largest in the entire solar system, Ganymede. This colossal world is even bigger than the planet Mercury, and in 1996, the Galileo spacecraft made a discovery that transformed our understanding of it. Ganymede was found to possess its own magnetic field, something no other moon has. The best explanation for how a cold, rocky body can generate a magnetic field is the presence of a large, global layer of electrically conductive fluid. For Ganymede, that fluid is a massive subsurface saltwater ocean buried under 90 miles of ice. This hidden sea is thought to be dozens of miles deep, held in place between layers of different types of ice under immense pressure. The sheer scale of this aquatic world is humbling, a reminder that oceans may be the default state for large moons across the galaxy, not the rare exception we once believed. Finally, we venture to the frozen edge of our solar system, to Neptune's captured moon, Triton. This world is a geological oddball with a surface of frozen nitrogen and a retrograde orbit that suggests it was once a free-flying dwarf planet from the Kuiper belt, snared by Neptune's gravity. Voyager 2's flyby in 1989 revealed a surprisingly young and active surface, dotted with mysterious dark plumes erupting into space. These are likely nitrogen geysers driven by the weak heat of the distant sun warming dark material just beneath the surface, causing pressurized nitrogen gas to explode upwards. But more intriguing than its surface activity is what might lie beneath it. Triton's density suggests it is a differentiated world with a rocky core. That core, heated by the radioactive decay of elements and the leftover energy from its traumatic capture by Neptune, could be warm enough to maintain a deep, liquid water ocean between the rock and the icy shell above. It is a long shot, a world on the frigid frontier, but it stands as a powerful symbol that the potential for habitable environments exists even in the most remote and unexpected corners of a star system. These 5 moons prove that the search for life cannot be confined to planets in a habitable zone. It must include the incredible, water-rich worlds that orbit the gas giants, reminding us that life may be hiding in the dark just beneath the ice. As we near the end of our journey through the top 30, we arrive at the frontier, not just of space but of discovery itself. The final spots on our list are reserved not for worlds we know, but for worlds we are almost certain to find, the next generation of discoveries that will be made by telescopes now on the drawing board. We begin with the ultimate prize, a category of world that has so far eluded us not because it's rare, but because it's incredibly difficult to detect with our current technology, a true Earth twin. This is the dream of a planet almost exactly the same size as Earth, orbiting a star almost exactly like our Sun, at almost exactly the same distance. We've found plenty of Earth-sized planets, and we've found plenty of planets in Sun-like habitable zones, but finding both conditions together around a G-type star has been the holy grail. The statistical evidence from missions like Kepler tells us they must be out there, likely in vast numbers. Finding one is the primary goal of upcoming missions, because only on such a world can we truly run the experiment of comparing its evolution to our own, to understand if Earth's story is a common one or a miraculous fluke in the cosmos. Beyond these perfect twins, astronomers are increasingly intrigued by the possibility of worlds that aren't just habitable, but super-habitable. This revolutionary concept suggests that some planets might actually be better suited for life than Earth is, and the most likely candidates are thought to orbit not yellow suns like ours, but stable, long-lived K-type orange dwarf stars. These stars are the Goldilocks of suns. They are more stable and longer-lived than our Sun, offering a potential haven for life for tens of billions of years, yet they are brighter and warmer than the flaring red dwarfs, pushing their habitable zones out to a more comfortable distance that may avoid the problem of tidal locking. A super-habitable world would likely be a bit larger and more massive than Earth, perhaps 2 or 3 times its size. This greater mass would allow it to hold onto a thicker atmosphere for longer, protecting life from radiation and creating a more temperate global climate through efficient heat distribution. Its stronger gravity would also fuel more prolonged volcanic and tectonic activity, ensuring a steady recycling of minerals and nutrients essential for a robust biosphere. Imagine a world with shallower oceans, sprawling archipelagos instead of isolated continents, a milder climate and a richer atmosphere, a planet where life isn't just surviving but thriving on a scale and for a duration we can scarcely imagine. Then we venture into the truly dark and lonely reaches of the galaxy to consider perhaps the most alien of all potential abodes for life, rogue planets. These are worlds that were flung from their nascent solar systems by gravitational interactions, and now they drift forever in the profound cold and blackness of interstellar space, untethered to any star. To our traditional way of thinking, these should be the most dead and frozen objects imaginable. Yet life may find a way even here. A large, rocky rogue planet, similar in size to Earth or larger, would not immediately freeze solid. Its rocky interior would remain hot from the residual heat of its formation and the ongoing decay of radioactive elements. This internal furnace could be sufficient to maintain a vast, global ocean of liquid water deep beneath a thick, icy crust, completely isolated from the frozen surface above. In this sunless abyss, life would not rely on photosynthesis but on chemosynthesis, drawing energy from hydrothermal vents on the ocean floor, much like the ecosystems found in Earth's deepest trenches. An entire biosphere could exist in this eternal, pressurized darkness, completely unaware that stars or galaxies even exist, living and dying in a warm, watery pocket surrounded by an infinite desert of space. The number of such rogue planets is believed to be colossal, perhaps outnumbering stars in our galaxy, meaning the most common form of life in the universe might not live under a sun, but in the isolated interior oceans of these nomad worlds. The key to unlocking these mysteries, to moving from tantalizing speculation to confirmed discovery, lies with the next generation of astronomical observatories. The torch will be passed from the incredible James Webb Space Telescope to a series of even more powerful instruments designed with one explicit goal: to find signs of life on other worlds. The most ambitious of these is the Habitable Worlds Observatory, a concept now actively being developed by NASA. This would not be just another telescope. It would be a revolutionary space observatory specifically engineered to directly image and analyze the atmospheres of dozens of Earth-like planets around nearby stars. Using a sophisticated internal coronagraph or a massive external starshade to block the blinding glare of parent stars, the Habitable Worlds Observatory will stare directly at these distant points of light and break their light into a spectrum, a chemical barcode that reveals the precise composition of their atmospheres. It is this barcode that will finally provide the answer we have sought for millennia. The telescope will search for the unmistakable combination of gases that, on our planet, are produced almost exclusively by life. It will hunt for the simultaneous presence of oxygen or ozone, which is rapidly consumed by chemical reactions unless it is constantly replenished, and methane, which is quickly broken down in the atmosphere unless there is an ongoing source. Finding both together in the atmosphere of a distant world would be the closest thing to a definitive signature of a living biosphere that we can hope to achieve from light years away. This mission represents the culmination of centuries of scientific progress, a direct pathway to answering the profound question of whether we are alone. The discoveries it makes won't just add to a list, they will fundamentally reshape our understanding of biology, our place in the cosmos, and the very nature of life itself. The future of this search is brighter than it has ever been, and the next chapter in this story will be written not in speculation, but in the hard, beautiful data of light from another living world. From the crushing pressures of Hycean worlds to the sunless oceans hidden beneath icy crusts, our tour of these 30 incredible worlds reveals one profound truth above all others. The potential for life is not confined to a single Earth-like template. It is a phenomenon of breathtaking diversity and stubborn resilience, capable of emerging in the eternal daylight of a tidally locked super-Earth, in the global methane seas of a frozen moon, or in the abyssal darkness of a rogue planet drifting between the stars. We began our search looking for a second Earth, but we found something far more thrilling, a universe overflowing with possibility, where the definition of habitable is limited only by our imagination. Each of these worlds, from our closest neighbor Proxima b to the ancient, time-worn Teegarden star B, tells a different chapter in the same grand story of cosmic evolution. They teach us that life is not a delicate miracle requiring perfect conditions, but a fundamental force of nature that seizes every available opportunity, adapting to extremes of temperature, pressure, and chemistry we once thought were insurmountable barriers. The building blocks of biology, water, organic molecules, and energy sources are not rare commodities. They are the common inheritance of countless worlds across the galaxy. What varies is not the ingredients but the recipe, and the universe has an infinite number of ways to combine them. This is not the end of the story, but merely the end of the beginning. The next decade promises to be the most revolutionary in the history of astronomy. With the James Webb Space Telescope already peering into alien atmospheres and missions like the Habitable Worlds Observatory on the horizon, we stand on the precipice of a discovery that will shatter our cosmic solitude. The data we gather will move us from speculation to confirmation, from wondering if life exists elsewhere to understanding what form it takes and how common it truly is. The greatest discovery in human history is within our grasp, and it will redefine our place in the cosmos. So the next time you find yourself under a clear night sky, take a moment to truly look up. Each of those twinkling points of light is not just a star, but a sun, a gravitational anchor for untold numbers of planets and moons, each with its own unique landscape, its own history, and perhaps its own living, breathing story. Let that feeling of wonder wash over you. Let it fuel your curiosity, for we are the first generation in human history with the technology to transform that ancient question, are we alone? From a philosophical dream into an empirical fact, this journey of discovery belongs to all of us. To make sure you don't miss the next great revelation, be sure to subscribe and hit the notification bell. The universe has kept its secrets for billions of years, but the veil is finally lifting, and the truth is more extraordinary than we ever dared to dream.